2.5, this is precalc. We are, let's just do a couple of these right now. It says that suppose that you are given all the pieces. No, now you have all the pieces. Let's work on them. This is like your homework last night. Then let's just suppose that the function is f. Describe how each one of these changes can be obtained from the original graph of f. So, if I'm looking at the first one of a, you would say it's f of x plus 4. You say what? What's it doing? No. It's up 4. Up 4. Because it's f of x plus 4. So at the very end, you're adding 4. Everybody just went up. Next one is f of x equal, or y equals f of x minus 2. It goes to the right 2. Next one is negative f of x. Does not go down. Not as in that, I wouldn't, that's not the correct terminology. It's flipped, yes. I'm going to say it's better, it's going to say it's reflected, not flipped. Reflected about, then you have to decide which axes is this going to flip. It does go down, so it's going to be the over the x-axis. It's reflected about the x-axis. The next one is y equals 3 f of x. It's a vertical stretch of 3. It's 3 times larger. These are all individual. These are all different things that we've talked about. And the last one, individual, before we start going all together here, y equals f of 1/2 x. What's this 1/2 do to my graph? It's not a vertical compression. It's a horizontal. Yes, it's a horizontal stretch of 2. It's going to be twice as long horizontally. You guys all see that? This is what we had to do in our homework. Now, I tried picking a few of them in your homework that dealt with a couple more items going on, but f says it's 0.5 times f of x plus 2 minus 1. So just list them all. These are important to understand, these changes. So, what do we see? Take it one at a time. 0.5. What's it doing?
Oh, it's going to be 5 times. Is this a 0.5?
That's a 0.5, yep.
Oh, it's a 0.5, so it's already.
It's a vertical shrink of, it's half the size. I'll let that one go with the half the size. A vertical shrink of half. It's half. What else we got going on? Left 2 and down 1. Works for me. No. Because the inside part is with the x first. It's kind of like most of your order of operations, inside out. So actually, that would affect your graph first, as in going left. Next one, negative 2 times f of negative x plus 1. It's negative 2, f of negative x plus 1. Just start on the outside. What's the negative do? Face down. I don't like that. We'd like to say something better. Reflected about x-axis. It's the negative inside now. Reflected about the y-axis. And the last piece says we are going up. Oh, yep, sorry, we forgot to talk about that. It's going up one, and it's a vertical stretch of 2. So the negative on that 2 just tells us that it's opening down or it's reflected about the x-axis. The 2 still needs to be stated, vertical stretch. About writing the last one down, it's 1/4 f of 2x minus 2. What's the 1/4 do? Vertical shrink of a fourth. The 2 in the inside says it's a horizontal shrink of half. It's half the size. And then the minus 2 at the end, down 2. So, before we get into actually starting to graph all of these, we actually need to sit back and talk about what's the most simplistic type of graph of each type of a quadratic, absolute value, square root, exponential, and logarithmic maybe, all of those types of things. I'm just trying to find all these different types of parents that you guys could potentially see, because we need to start someplace. And so we're all going to originate from these parent graphs. Okay? So what we'll do is I'm going to quickly sketch, what a log, each one of these looks like, and then give what a t-chart should look like. Because that t-chart is the one we're going to base everything off of, one step at a time. Everybody should know that a quadratic looks like that somewhat, yes? And if I was going to make a t-chart like the very first time we ever did this, you guys would have used your Fab 5. -2, -1, 0, 1, and 2, yes? And when I square all those, I end up with the values of 4, 1, 0, 1, 4. Okay? That should be a no-brainer. We all can make that happen. Going to absolute value. Absolute value graphs look like what? A V. Still centered at 0, 0. So when I make my t-chart, I still can use my Fab 5. Which, though, I'm taking the absolute value, not squaring, so therefore you get 2, 1, 0, 1, and 2. Correct? Those are pretty straightforward. I get to use my Fab 5s. Then I roll into something of the square root functions or the cubed root functions. It just doesn't matter. I'm using square root here. You guys can figure out the rest. But remember, square root functions look like they took a quadratic, cut off in a leg, and it falls over, right? So it looks like this. So all of our graphs are going to be based off of certain things. What was the conditions for a square root, though? Has to be positive, starting at 0, and if I'm going to get to choose my values, I will put what kind of values in. Perfect squares, so 1, 0, 1, 4, and 9. So I get 0, 1, 2, and 3. I'm going to purposely choose values that start nicely, so hopefully they stay nice. Not always going to happen, though, guys. Exponential. Ooh, what's an exponential graph look like? Yeah, something like that. Remember, you have an asymptote at 0, y equals 0, something you can't be at, and it starts low and goes high. That's if it's exponential growth. If it's decay, it goes the other way. So, y equals b to the x. That's your parent. Here's the cool thing about parents. They always have y equals 0. They always have 0, 1. 0, 1 would be your, not the origin. 0, 1 is that point that's crossing the y-axis. That's y-intercept. And then, now this is where it gets kind of a little tricky, is that if it's growth, so maybe let me take these away. If it's growth, I put 1 comma, and then whatever the value is when I put 1 in. If it's decay, I'm going to put -1 in. Okay? Because we can see, we know what's going on over here. When it's growth, this line is going to continuously go further and further and further, closer and closer to 0. You'll never be 0 because you can't start with something and multiply it to itself to get 0. It doesn't work that way. You'd have to be 0. So that we know what's going on. We don't know where the tail, I call it, is going. And so when it's growth, I pick a point that's on the right side so I can kind of keep track. Where's the tail? When it's decay, the tail's on the other side over here, and so I want to know where that tail is. That's why I put 1 or -1 in, depending on what b is, which is growth or decay. Okay? But you only have 3 things to worry about for exponential growth or decay. Same thing for log graphs. Log graphs are just the inverse of exponentials. So that means all of your x's and y's are switched. And so you now have, to make this a little easier, x equals 0, 0, 1, and you will have some points mixed up. Now, the way I actually go about graphing a log graph is just an extension of exponential. I'll find an inverse first, work with an inverse, and then switch it all back. Remember, inverses of points are switching x and y, which are very nice. Same thing for equations. Switch x and y and solve for y. And so, you have different graphs where you'll either have 1 or -1 going in. Okay? So when we get to that one, it's going to be slightly different, but now x equals 0 is a vertical line, and if I remember correctly, it's been a while, I think it looks more, nope, I don't think it goes that way. I think it goes this way. It goes this way. It's been a while since I graphed a log. So it goes that way, where it approaches x equals 0. So each one of these guys, we are going to take our parent first. We're going to find it, and then we're going to modify it several different ways, using what we've just done on the last couple slides and talking about those things. Are we ready for the next page? Because this is it. This is the stuff. Pay attention. Okay. This is the parent-family-child method. I picked this up from a teacher a couple years ago, and the way he did it was he just put a bunch of points on here and said, do this first and then do this second. He didn't have this little catchy name for it or calling it some kind of method. But so what I tried to do is try to relate it to something that we can remember and put some kind of form to it other than just do this because I said so. And the way you have it is that the method allows us to have a pathway to graphing complicated functions in transformational form. So all of these parents, or all the equations that we're going to be given, not all of them I guess you'd say, but 99% of them are going to be given in a form where you guys would recognize all of those changes of translated left, right, up, down, vertical stretch or shrinking, horizontal stretching and shrinking, in those forms. Okay? And it says this method always starts with a parent graph, then using order of operations, which I've kind of hinted at a couple times. Each transformation learned is applied with the ones multiplied going first and then adding last. Here's the cool thing. We're going to find a parent, we make that t-chart, and then we start applying each rules as we go along to it. Now, the way I have this is how I want to have it set up every single time. And it says you need to show both the steps, and I need to see the words. So you need to put these words on top. What I couldn't do on the computer was draw these little bridges. I like to sometimes draw bridges, and not even putting arrows on them. So I bridge them together, and on the bridge, I will write things like horizontal stretch or shrink of, vertical stretch or shrink, reflected about the x or y axis, translated h units left, right, k units up or down. If a translation is not there, or transformation is not there, you don't talk about it. If there is no up or down movement, you don't have to state it. You don't have to state no movement up or down. Just don't say anything. You only state things that are happening. Now notice, order of operations. What comes first, multiplication or the additions? Multiplications. Guess what letter comes back first? A. And actually, I possibly should have put a B inside here as well. So, let's do that. I think we should put the B inside. So f of bx. So A times f of bx. The A and the B come back first. You need to talk about your vertical and horizontal stretching, shrinking, and any kind of reflections first. Now here's the thing. If I am stretching something vertically, are my x values changed? Am I doing anything with my x's? Move your hand vertically. Do you go sideways at all? No. So therefore, if there's only a vertical movement, your x's are unchanged from your parent. Okay, it's going to make more sense when we actually put a problem to this. But you'll have a t-chart here. This t-chart will lead us to this t-chart with the effects of A and B. A affects your y's only. B would affect only your x's. And once you've created this t-chart, you will stop and you will continue, or you will not use the parent anymore. We go to the family one, and we use that one to find the child. Okay? Here's the thing. Multiply by A. Multiply. I don't like that. Too squeezed in there. This one is multiplied by 1 over B. Wait, why 1 over B? Why would that one have to be multiplied by 1 over B? Because it's with x and it always does the opposite, right, or the inverse. So when there's a 2 there, you're really affecting the graph by half. Okay? Then I can move over to the child. H and K. H is my left-right movement. That affects my x's. So you can add, subtract H to my x's. You can then take K and add or subtract it to my y values. Depends on if I'm going up or down, left or right. If I'm going left, I will take my x values and subtract them. If I'm going to the right, I add to my x values. Again, once we start doing a problem, you start hopefully seeing the steps all roll together. Okay, guys, this is what I consider a child graph. It's got a lot of moving parts on here. Okay? So our first order of business is we need to establish what is the parent graph of this. The parent graph, guys, and I need to write that, parent is y equals, it's x squared. I need to remove all of those extra pieces that we've been talking about the last 2 days. Yes?
Are we doing that?
Okay. So now that we know this is our parent, we will then create its t-chart. Going back to the slide from before, or we should know this one hopefully by heart, is the fact that I would use my Fab 5. And plug them in to x squared, you would get 4, 1, 0, 1, and 4. Everybody should be okay with that. We just found its parent. I like to sometimes think of if you have a problem with someone's kid, what do? You go find their parent, and if the parent is still having trouble with their kid, they're going to go talk to their family before they go deal with their child. Okay? So it's kind of like the order of how we should do these things. Now, I now need to get to the family. So I build a bridge. The bridge tells us in words what's going to happen to get to that family. Family, guys, remember, brings back the A value and a B value. Is there a B value?
No.
There's no B value, so guess what I'm not going to talk about? Anything that's associated with a B. Now, A, there is a A value. It brings back A. So when I bring back A, it now looks like 2x squared. Right? And now on that bridge, you tell me what the 2 does. What does a 2 do? What does that particular 2 in front of the function do? It would be a vertical stretch of 2. So I need to hear these things. A vertical stretch of 2. Now, as I was saying before, if I stretch something vertically, what are the only values that get affected? Just the y's. So guess what? All of the x's are going to stay the same. And according to the last page, all I need to do is take that 2, take the 2 and multiply it to your y values to get your new ones. So, 4 times 2. 1 times 2. 0 times 2. So it's 8, 2, 0, 2, 8. We're over halfway done, guys. The next step is to get to the child. The child is the actual equation in question. So I just write down the whole thing. And it brings back the h and the k. And what does the h do? It's 2 right and 3 down. I base this off of the family that if I go 2 to the right, all of my x values in this graph will all be moved to the right 2, which means I take them all and do what? Add 2. What's negative 2 plus 2? Negative 1 plus 2. 0 plus 2. And 3 and 4. I added 2 to all of my x's. What am I going to do to my y's then if I go 3 down? Subtract 3. So now I'm at 5. 2 minus 3.
-1.
Negative 3. Negative 1. 5. Hey guys, what was h and k again? What's h? 2. What's k? What's in the middle of that t-chart?
3.
Which is called the
Vertex.
vertex.
Isn't 3 minus 3 0?
Where are we? 3. I agree 3 minus 3 is 0, but...
Never mind.
Okay. Now, all you have to do, guys, is graph this t-chart. You have now graphed that equation. You do not need to make a complicated table or anything like that.
That's a lot.
0, 5, 4, 5, 1, negative 1, oh, negative 1, and negative 3. There's your graph. Guys, this problem right here is your only homework. Have a great day.